A graph traversal is a procedure for systematically going through all of a graph's vertices and edges. When you think of a graph, you may think of something like the graph shown here, which is about 7 vertices and 7 edges. And you may wonder, why do you need a formal procedure when it's obvious how many vertices and edges there are? But in many real-world applications, the graphs are much larger and look more like this. For example, a social network can be represented as a graph with people being the vertices and the connections between people as the edges. Such a graph will have millions of vertices and hundreds of millions of edges. So if we need to explore such a large graph, we would need to do this systematically with an algorithm. The first challenge when we traverse a graph is to make sure that we don't get stuck in a loop, because large graphs will likely have several loops. We also want to make sure that our algorithm is efficient in both running time and the space that's required. There are two main graph traversal algorithms. One is called depth-first search, and this algorithm visits child vertices before sibling vertices. This small graph illustrates this. Let us say I've already visited the 2 vertices shown in blue, and I'm currently at the second node. Depth-first search will choose to move towards a child node before moving to the sibling node. This is in contrast to the second approach called breadth-first search, where you visit the sibling vertices before the child vertex. The two algorithms are similar, but they use different data structures. Depth-first search uses a stack or is implemented as a recursive function, while breadth-first search is implemented with a queue data structure. In this presentation, we look at breadth-first search. The main idea of breadth-first search is that we start from some vertex, then we visit all the nodes one step away from that start node before moving further away. Then we visit all the nodes that are 2 steps away from the start node, and only after we have done that do we move to nodes that are 3 steps away from the start vertex. This is a pseudocode for the breadth-first search algorithm. This implementation uses 2 data structures, a queue, sometimes called a frontier queue, and a set to store whether a vertex has been visited or not. Initially, we mark all our vertices as not visited and store them in the set. The start vertex is pushed onto the queue, and the start vertex is also marked as visited. The algorithm then enters a while loop that continues until the queue becomes empty. In every iteration, you pop the vertex at the front of the queue, and that becomes a current vertex. You then look at all the neighbors of the current vertex one by one. If a neighbor is marked as not visited, then we mark it as visited and insert it to the back of the queue. This iteration then ends, and then these iterations will continue until the queue becomes empty. The algorithm will become clearer when we go over an example. But before that, you will notice that the for loop in the algorithm does not actually specify the order of adjacent vertices. The order does not matter, that is, any order will be a correct traversal. However, for consistency, if you want to get the same answer as everyone else, we will need to select certain vertices in some particular order. The alphabetical order of the vertex label is one simple way of doing it. This is also called the lexicographic order. We'll follow this lexicographic order when we go through the next example. So here's the graph that we want to explore. I want to do a breadth-first search starting from node A. So initially all the vertices are marked as not visited except for the start vertex, which is marked as visited. A is also inserted into the queue, and now I'm ready to start the iterations. At every iteration, I'll pop the front of the queue, and that node becomes the current node. So I pop A, and A becomes the current node. A has 3 neighbors, and none of them have been visited. So we mark these vertices as visited and insert them to the back of the queue. So notice that I insert them in lexicographic or alphabetical order. So first C, then D, then H. After this, we are done with the current node A, and for the next iteration, we'll pop the front of the queue, which gives us C, and C becomes our new current node. C has 3 neighbors, but only G is not visited. So we mark G as visited and insert G into the back of the queue. The edge between C and D that connects the current node with a node that was previously visited is called a back edge and indicates the presence of a loop. For the next iteration, we again pop the front of the queue, which gives us D, our new current node. D has 5 neighbors, but only B is not visited. So we mark B as visited and insert B to the back of the queue. The edges between D and H and D and G connect the current node with a node that was previously visited. Such edges are called back edges and indicate the presence of a loop. For the next iteration, we again pop the front of the queue, which gives us H, our new current node. But notice that all the neighbors of H have been previously visited, so there is nothing to be done at H. And to move to the next iteration, we again pop the front of the queue, which gives us G, our next current node. All the neighbors of G have also been visited previously, so there is nothing to be done at G. So we again pop the front of the queue to get B as our next current node. Again, all the neighbors of B have already been visited, so there is nothing to be done at B. And as the queue is empty now, the algorithm ends. I've also shown the order of the visits of our vertices at the bottom of this slide, and you can check that at the end of the algorithm we have visited all of the vertices, and you'll also notice that we visited the nearer nodes first before moving on to the farther nodes. Next, let's look at the complexity of the running time and the space of breadth first search. Let V represent the total number of vertices and E the total number of edges in the graph. So these two numbers are a measure of how large our graph is. Let's also assume that changing the label of a vertex from visited to non-visited takes some constant amount of time, that is O of 1. Notice that this algorithm labels each vertex twice. Initially all the labels are marked as not visited, and then over the course of the algorithm the vertices become visited one by one. So the total cost of this step in the algorithm is O of V. Notice that also in every iteration we have to push all the adjacent vertices of a vertex into the queue. The number of adjacent edges or vertices is called the degree of a vertex. There is a theorem about graphs which says that the sum of the degrees of all vertices in a graph is twice the total number of edges. So we can use this result to say that the total time taken to complete the for loops is O of E, and the total time to run this algorithm is O of V plus E, which means that the running time of breadth first search is proportional to both the number of vertices and edges in a graph. By the way, this assumes that the graph is represented as an adjacency list, which means that we can get all the adjacent vertices in time proportional to the degree of the vertex. Not all graph representations are capable of doing this. The space complexity of breadth first search is O of V because the set data structure needs to store whether every vertex is visited or not. This space requirement is a serious limitation when searching very large graphs. The most important property of breadth first search is that vertices are visited in increasing order of distance from the start vertex. Thus, when we reach any vertex, we also know the shortest path from the start vertex to that vertex. Thus, breadth first search is useful in applications that need to find the shortest path, for example in certain communication protocols on the internet. Another application is to recommend new friends on a social network. In a social network graph, vertices represent people and an edge connects two people who are friends. And the start vertex is you. Your friends are all the vertices one step away from you. And friends of your friends are exactly 2 steps away from you. And breadth first search can be used to identify these friends of friends. Social networks often recommend friends of friends as potential new friends to you.